Welcome to video 2, where we're going to kind of cover the acid and bases imbalances and introduce you to some of the compensatory mechanisms associated with that. So an acid-base imbalance is very simply defined as when intake doesn't equal output for either acids or bases. So either hydrogen ions or the bases that bind those ions. Okay, and whenever you have an imbalance in those molecules, you get a change in pH, and so that is defined as an acid-base imbalance. Your regulatory mechanisms react to those changes to try to minimize them or correct them. Okay, basically they detect change in pH that results from this imbalance, and they try to correct that change. All right. So some examples, we can generate an acidosis or an alkalosis through hypo or hyperventilation. Anything that basically affects the ability of the lungs to get rid of CO2. So if that ability is inhibited, then CO2 builds up and you get an acidosis. So CO2 goes up, and you take this carbonic acid equation and you shift it to the right so that more carbon dioxide combines with water to generate more protons. And so your pH goes down, your hydrogen ion concentration goes up. If the CO2 drops, because for instance you've increased your respiration rate and blown off more CO2, the CO2 will then drop, and this equation will be pulled to the left so that more bicarbonate will combine with more hydrogen ions and you'll generate more water and CO2. And so your pH will go up and your hydrogen ion concentration will drop in that case. Okay? Renal failure, as you guys know, the kidneys are responsible for getting rid of a lot of these molecules, including the hydrogen ions themselves. Bicarbonate can be reabsorbed and actually produced in the kidneys, or it can be excreted depending upon the pH. But in any case, these two are definitely handled by the kidneys, and a lot of non-carbonic acids are handled as well. So if you have a renal failure and you reduce the kidney's ability to handle these molecules, you can get an acid-base imbalance. Okay? So we can also get an acid-base imbalance when we lose fluids in the body that aren't a physiological pH. So for instance, your stomach has a lot of acid in it, hydrogen chloride, and if you vomit a lot, you're going to lose that hydrogen chloride. So that is ultimately going to drop the hydrogen ion concentration in your body and result in an alkalosis where the pH actually goes up. Okay? On the other hand, you can lose a lot of alkaline fluid through diarrhea, a lot of bicarbonate in particular. That will decrease the amount of base in the body, and that will result in an acidosis, an increase in the hydrogen ion concentration. So you can get this imbalance simply by losing fluids. Now, if you lose fluids that are pH 7.4, you won't really be losing an excess of base or an excess of acid, but ordinarily that's not the case, as you can see here. Okay. For instance, if you hemorrhage, that's a different story. You're losing the plasma. The loss of the plasma itself won't cause an acid-base imbalance. All right. So we can have metabolic changes that can, for instance, cause lactic acid accumulation and hypoxemia. And you can get ketones in diabetes again. These will result in an acid-base imbalance through the generation of more acid. So these are acidoses. So we can take these and we can classify them. First of all, acidoses are defined as any condition where the pH drops below 7.37 of the plasma. Now, normal plasma is 7.4. So you can see that it doesn't have to drop much for you to get an acidosis, and the same thing goes for alkaloses. If the pH gets above 7.43, that's an alkalosis, but that's not that far from 7.4, which is smack dab in the middle of normal, okay? So the pH has to be fairly highly regulated. So let's talk about the acidoses first. A respiratory acidosis is when you get an increased partial pressure of carbon dioxide in the plasma. So in this case, high carbon dioxide will shift this carbonic acid equation to the right, and you'll generate more hydrogen ions and your pH will drop, and that is a respiratory acidosis. A metabolic acidosis is basically anything that's non-respiratory. And ordinarily what we're talking about here is an increase in some non-carbonic acid or a decrease in the availability of base, and that decreased base can include bicarbs. So here we have our hydrogen ion bound base in solution that dissociates into hydrogen ions and your base here. If you lose this base, you're going to pull this equation to the right, you're going to increase the amount of free hydrogen ions. And of course, if you just add more H base, you'll generate more hydrogen ions as well. Okay, so that's a non-respiratory, a metabolic acidosis. Alkaloses are also respiratory and metabolic. In the case of a respiratory, it's the opposite of the acidosis. If you drop carbon dioxide, you pull this equation to the left, and you lose protons in that process. You lose hydrogen ions, and your pH goes up. On the other hand, if you are losing non-carbonic acids or these bases, then what will happen is you will decrease the hydrogen ion concentration. If you increase the base, decrease the non-carbonic acid, you will increase hydrogen ions, okay? Either you're decreasing on this side, which pulls this equation to the left, or you're increasing this base, and that pulls this equation to the right, okay? And either way, you're getting more hydrogen ions, or fewer hydrogen ions, excuse me. Increased base shoves this equation to the left, decreased H base pulls this equation to the left, okay? All right. So we have two ways to correct an acid-base imbalance. One is through buffering, and you should recognize that this is a temporary fix, and it does not reverse the change in pH. What it does is it decreases the impact of added acid, let's say, to the plasma, so that the change in free hydrogen ion concentrations isn't as great as you might expect. And I'll talk about that in a second. But you should notice that this won't actually correct the imbalance. If you want to correct the imbalance, you have to go into what's compensation. And that actually returns the pH back to normal, usually through changing carbon dioxide respiration in the lungs, or through changing excretion through the kidneys. We'll talk about that in a minute. We'll talk about it now. Here's sort of an overview of compensation. Now we're going to talk about this in detail in lesson 3 of this series. But basically, here's your carbonic acid equation. And what's happening is your hydrogen ion concentration is being changed by either changing carbon dioxide through the lungs, or by changing the bicarbonate through the kidneys. All right? So in the case of the lungs, if you have, let's say it's an alkalosis, one thing you can do is slow your respiration. That will cause carbon dioxide to build up. That will shift this equation to the right, and that will increase your hydrogen ion concentration and bring the pH back toward normal. So that would be a compensatory response, okay? In the kidneys, if you have an alkalosis, then one thing that you can do is reduce the excretion or increase the excretion of bicarb. That will drop this bicarb concentration, shove this equation again to the right and increase your hydrogen ion concentration and bring it back to a normal. So you can compensate either way. You can up this side or decrease this side. The kidneys and the lungs work together to make that happen, okay? And you should recognize that this is corrective, pH is not. So this will actually change the hydrogen ion concentration and actually bring it up toward normal, okay? That is as opposed to buffering. Now, buffering is when you increase a base that binds hydrogen ions, okay? So when you do that, you should recognize that you don't prevent the pH from changing. What you do is you minimize the magnitude of that change, and I'll show you that in a second. It's not a permanent fix because there's only a limited amount of buffering molecules in your body, and the more that you use up by binding to hydrogen ions, the less is available to bind more. So ultimately, to sustain the ability of a buffer to help you out with this and minimize the changes in free hydrogen ions, you need to eventually restore the buffer that is binding the hydrogen ions. In other words, this can't be a permanent binding. Eventually, you have to get rid of the hydrogen ions some other way so that you can restore the amount of base that's doing your buffering reaction. So let me show you what that means. Here we have a beaker, and it contains bicarbonate and hydrogen ions. And you can see here we have 3 free bicarbonate molecules. They're this blue color. All right? And if we add acids, 3 hydrochloric acid molecules to that beaker, we get these hydrogen ions, which are black with a white dot. They actually bind to bicarb, okay? So you can see here's 2. We had 3 free bicarbs here. Now 2 are bound and 1 is free, okay? Now if I added these 3 HCl's and there was no buffer, you would just get hydrogen ions and chloride free in solution, and you will have added 3 free hydrogen ions to the solution. As it is, you have added those hydrogen ions. They have bound bicarb. 2 of the bicarbs bound hydrogen ions. 1 became free. Okay, so we minimized the change in pH by binding 2/3 of the molecules that we added. Okay, so this is a typical buffering reaction, and this is one way that you can minimize the impact of added acid to the system. Okay, the disadvantage is, of course, here we had 3 bicarbs that were free. Now we only have 1 that's 3, and so if we added more acid, we wouldn't be able to bind up a whole lot more of these hydrogen ions because we used up 2/3 of the bicarb that we had, of the free bicarb that we had in the solution, okay? So if you want this to continue to be effective, eventually you have to get rid of these hydrogen ions and re-free these back up so that they're available to buffer again when needed, okay? So some available buffers, the primary one is bicarb associated with the carbonic acid system. This is a plasma buffer, okay? A close second to that in terms of its impact on the system is hemoglobin. Hemoglobin binds to, as you know, binds to hydrogen ions, and that can be a fairly significant rapid buffer. It's a close second to the bicarb in terms of its overall impact, and that's going to have an effect on our. That's going to be a major buffer that we'll have to address later on in some of the later lessons here. We also have intracellular proteins and phosphate, which bind to hydrogen ions, again, mostly intracellularly, but they're fairly important buffers as well. And then we finally have plasma proteins, which are less important because they're at a less concentration than the bicarb and the hemoglobin, but nevertheless they have an impact, okay? And finally, we have bone carbonate. That's released from bone in the presence of an acidosis. It's really, really slow, but it happens. And this carbonate eventually becomes bicarb and participates in buffering, okay? So you can think of this as being bicarbonate. So let's talk about, now that we've talked about these buffers, let's talk about the time course of the response to a change in pH in our third video.